Well, today's lecture is on systems engineering. Thursday is on you get what you measure, meaning when you set in a rating system, you have a great deal of effect on the system, and you get, finally, surprising results from what you measure. The next one is not in the notes. It's on how do we know if we know it. It's an attempt to answer the question, when science says we know or we have proved, just what do we mean? What do we mean when we say we know so-and-so? Technically, it's called epistemology. Next Tuesday is the final lecture on you and your research. It's a talk I've given many times, and you can say, in a certain sense, this whole course is an expansion of that talk. Or alternatively, you can say that talk next Tuesday is a summary of the course. Now let's get back to systems engineering. Now, a parable is much more effective frequently than is a direct statement. So I'm going to talk about a man who was looking at a cathedral being built. He went and talked to a guy who was chipping stones, said, "What are you doing?" He said, "I'm making stones." He went to a sculptor and says, "What are you doing?" He said, "I'm carving gargoyles." He went around and asked each person said what they were doing. He finally came to a little old lady who was sweeping the floor. And he asked her, "What are you doing?" She said, "I'm helping build a cathedral." Now, if on the ordinary campus you ask a professor at random, "What's he going to do?" He said, "Oh, I'm teaching partial fractions. I'll teach Young's modulus how to measure it, or I'll teach something else." Rarely will he say, "I'm going to educate the students for their future." Now, you may say in both the parable and that story that, of course, the bigger goal was always understood. But I doubt that you really believe it. Most of the time, people are so meshed in the details, they fail to see the bigger picture. It is the essence of bureaucracy. The bureaucrat does his job in front of his face the way he sees it. He does not see the larger function of the whole organization. It's very common. Well, systems engineering is an attempt to look at the whole as a whole at all times. That's what system engineering is. It's an attempt to look at the whole as a whole and not make these foolish mistakes of trying to think it's the details. Now, it's not easy to be a system engineer. It's very hard. But because system engineering is very popular, a large number of people have learned how to say the right words. But you're familiar with people who know how to tell you all about how to play tennis, but they themselves cannot play a good game. The same in system engineering. You don't pay attention to the person's words, you judge them by what they produce. And there are very few actual good system engineering, but there are a large number of people who can say all the words. So I claim to you the problem is very, very difficult. You know what you want to do perfectly well, but you cannot do it. And you may be surprised at this, so I'm going to turn right on a whole bunch of you. You know you're here to get an education. You know the people paying the bill, the teachers, and you yourselves all believe the education is going to do you some good in your future career. Otherwise, we wouldn't be doing it. You know it's an education. Nevertheless, every term you cram at the end of the term, you know that is counterproductive to your education. You know the same effort spent all along the way reasonably should be what you're doing, and cramming is counterproductive. It simply crams a bunch of stuff in which tends to fade out promptly. It's very poor policy. You know it, but you can't stop cramming. You try to get the grades term by term by term, course by course by course, without looking at the whole picture. Thus I say, you know what the system is trying to do, namely produce an educated person. But you cannot follow your own rules. You practice inefficient, counterproductive techniques which go against the system. That's why system engineering is so damnably hard. You may perfectly well know and believe, but you can't follow your own rules. That's the tough thing. System engineering is the attempt to keep at all times the larger goals in mind and to translate the local actions into global actions. But there is not a single larger picture. It's one of the many troubles. Take, for example, I told you when I first got control of a digital computer at Bell Labs. I thought my task was to get the maximum number of computation done per day. What better? Keep the machine busy, get the numbers ground out, don't stall around, don't let my machine stand idle. My God, it's there to be used. After a while, it dawned on me that it was really important to do important computations, and non-important ones, it didn't matter. My problem was to find the important computations, those which would matter to Bell Labs, and to avoid those that would not. Now, I was in a research department, math department, so I naturally started in the math department. But I began to look at the research department. Well, now, if the research department were going to use a machine efficiently in those days, it gradually dawned on me the scientists had to ask the right questions. Otherwise, the problems are no good. How will I learn to write the right questions? How will I know to ask them, write them down, or wherever you want? Answer, probably only if they come to terms with the machine and learn how to run it themselves. The machines were so different that they're not hand calculation. So I had to set out a method of programming that was so easy that the staff would have to learn how to run the machine, to learn how to do simple computation and what machine computation meant against hand calculation. It's a different business. Well, after a while, it dawned on me that I was not only employed by the math department and the research department, I was employed by Bell Labs. Therefore, part of my problem was to provide a service for the whole of engineering, to find out what computers could do with the breadth of engineering. I also began to realize my task was not to do the computation, it was more to find out what could be done, show people how to do it, and let them build on what I had found out. My task was really not to compute, but to find out how machines should be used. Well, above Bell Labs, there was AT&T and Western Electric. What about them? What about the whole scientific world? What about the whole world? I have obligations to all those levels. And the obligations are short-term, relatively long-term, and very long-term. Very different obligations again. To get some computation done today, or find out how to do computing in some area so we can do it tomorrow. I have all those conflicts. I have a job as a total system, and you can't say where the boundary is at any one moment, but that's the real position I was in, and that's the position you were in almost all the time. Now, it's very easy, I said, to say the right words in system engineering. You can even say them to yourself. It is very hard to practice it. I found myself in constant conflict, worrying, am I doing the right thing? Am I spending too much time on the immediate versus the long term, or am I spending too much in the long term and not immediate? Am I not educating people adequately, besides getting answers? What about the effect on AT&T? Had we not better do things to get AT&T alerted that machines are coming along? Have we not obligations in many other directions? I had to balance these things, and it was not an easy task. Now, the first rule of system engineering is one which you won't believe. If you optimize a component, you probably ruin the system's behavior. Now, that sounds very strange. I've got a system, a whole bunch of components. I make one better, the system performance goes down. Since it's very hard to believe, I'll tell you a dramatic story with regard to the differential analyzer. I had inherited the differential analyzer. I'd gotten it because the original guy was so incompetent. I could bound to look better after he did it. And I did it so well, we had so many problems that gradually we needed another machine. Both so we could couple the two together to get bigger problems done, and B, so we could do more problems, because we were now overloaded. Well, we couldn't buy them commercially because they weren't quite good enough, so we had to have more M9 gun directors condemned and built on the shop floor at Whippany. And I'm to go over and look at it in this acceptance test, so I'll move it over to my place. I get a friend of mine to look at the system with me, and I try first the well-known equation, y of 0 equals 1, y prime of 0 equals 0. whose solution you know is the sine. And the derivative is the cosine. If you plot the sine against the cosine, you should get a circle. And how well the circle closes on itself time after time after time tells you how accurate the machine is. Well, we patched up the first one, it doesn't run. Well, it must be one bad component someplace. We picked some other components, tried again. Didn't work. After 2 or 3 tries, my friend admitted something was wrong. We called in the guys who assembled it, pointed out to them that something was wrong. They had to admit there was something wrong. And so my friend and I watched. And we finally got bored watching. We went to lunch. We came back from lunch. They had found the trouble. Yes, they'd put in better amplifiers, much better amplifiers than the ones I had. What they had not done was put in adequate ground. What was happening is the leakage through the inadequate ground from one amplifier to another was wrecking the whole system. All they had to do was put in a really heavy copper bar, and then the thing ran. Now here's a machine where all the components are independent, and still improving a component ruined the system behavior. I know it sounds strange. You say, oh, that's a unique one. No, it's not. It's very, very common. It's very common that when you improve a component, the system goes to hell. Now let me give you some examples. Again, take mathematical reform. We've had a 30 or 40 years now of reform of the calculus. What they do is have some idea, like use computers or something else, and they do that. They never, never ask themselves, what is a total mathematical education? Now, to be mathematically sophisticated, you certainly ought to know math induction. And you ought to know complex numbers, and so on. But what happens in these things? In complex numbers, you meet them in high school algebra when you hit a quadratic. And then I say in holy dread, they are avoided. Calculus never mentions them. Geometry never mentions them. Until you come to linear algebra. And they're well into the thing when you suddenly hit complex eigenvalues and complex eigenvectors, you meet them again. Now you're facing 2 difficult concepts, complex numbers and eigenvalues and eigenvectors. And is it a wonder that the students go to park and don't know what's going on? No. You never try to teach 2 complicated things at one time. But there they do, because they did not stop and think. Yes, we must deliberately give the reinforcements steadily on complex numbers so when we come to this point, they will understand them. The same thing happens in math induction. You're told a couple of times, and then for a long while you never meet it, and finally, if you take computer science, you'll meet it frequently, and you find other words now and then. It's a basic tool for answering the question, how, under mathematical conditions, can I prove something for all cases? It's a fundamental method of reasoning, and it's important that you understand both what it can do and what it cannot do. Well, they don't do that. They don't look at it. What they've done instead is they've optimized calculus, and they optimize linear algebra, and they optimize other courses. As a result, you don't have a decent mathematical education. Now, their excuse is quite simple. The whole problem, namely what is a mathematical education, is too big to think about. Therefore, let us do what we can do. That's the typical technician. They will not stop and think. Now, the same thing happens with most of this faculty. I don't think you could ever get out of this school a statement of what the educated output is supposed to be. If we don't know what the output is supposed to be, how the hell are we supposed to do a good job? With difficulty. This is one, again, example of the failure to look at the system and the consequent trouble. So I began to think about the history of systems engineering. The earliest example I know is between 12 and 1400 in the arsenal at Venice. They had a line coming down, they produced the ships, the masts came in, the sails came on, the oars came on, this came on, and a train crew was there. They got in a boat and left. It's an early example of just in time. Just in time the mast was there, just in time the sail was there, just in time the oars were there, just in time the train crew is there. That is an example of systems engineering. They knew the system, they knew the problem, and they looked at the whole problem. How do I keep a fleet going? It's more common now, but that's the first one I could find in history. Now you may say that the railroads were systems. Yes, but that does not mean, I think, that you can look and say the guys who built the railroads understood the system. When I read the history, I doubt that they did. They saw the locomotive, they saw the cars, they saw the rails. They did not think of the system as a system. They simply patched piece here, piece there. The first real system engineering that arose in large in modern times is the telephone company. They were in a very funny position. They not only designed and through Western Electric manufactured, but they operated it. Now there's a big difference between making something and selling to somebody else and running it yourself. A tremendous difference. Suddenly reliability and other things and maintainability become very, very large because you're going to have to do it. And since it's the same organization, it enters into design. Now I have to tell you something about the telephone business that probably never occurred to you. It's called the diseconomy of scale. You're used to the economy of scale. If you want to build 10, it's one thing. You want to build 100, you can gain economy by scale. But now consider the telephone business. We have 10 subscribers. 11th one comes in. That 11th one's got to be connected to the other 10. A 12th one comes in. That 12th one's got to be connected to 11 other people. The more people there are, the more cross connections I must produce. It is a job which is very easy to do when you got 2 people. It's very hard to do when you got 200 million. They had that peculiar problem of the diseconomy of scale. The bigger they got, the relatively harder it is to do the job. Not the easier it is. So they had to pay attention to system design, and I will say by and large, they have done it pretty shrewdly. In fact, they've done it so shrewdly now that most of you haven't got much idea. You push the buttons there and you get connected, and haven't much idea what happens behind it. They've got a big, elaborate system going there, a very complicated one, probably the most complicated thing built still to this day. Every central office has well above 1 million lines of instruction now. It used to be mechanical. We've got them into computers. But we face the problem of how do you produce 1 million lines of code twice a week or oftener when no 2 central offices are in the same place at the same time or doing the same function. Central offices don't do the same thing. Some of them have different calling habits. Ones in cities, you have different calling habits than you have in the country. You have different design criteria to meet, and therefore the software must be different. They face these problems, and by and large, as you know, it works. It works better in electric distribution because when the power fails, you grab the telephone and suppose you can call up and tell them, hey, the power's out. You'd think it would be the other way around, wouldn't you? But nope, that's the way it goes. It's pretty good. Now, I don't pretend to answer the question how it was that I, who was a classically trained pure mathematician, became a system engineer. But I can give you some episodes along the way. As a junior, when I went to Chicago, Robert Hutchins, the radical president of Chicago, was in charge. And the rule was you got a degree when you passed 9 courses in your major field and 6 in the minor. It didn't matter what grade you got along the way, you had to know the stuff at the end of your senior year. You had to know the 9 course of mathematics. Well, that makes you study a little differently. When you are told you're not passing course by course, you're going to know the whole as a whole on an exam then, and your minor field you're going to know the whole as a whole there. It makes you think a little different, it makes you study different. The next big episode was at Los Alamos, I think, when, well, of course you do it partly when you get your doctor's degree also, you begin to study the problem of how you're going to pass your orals. But at Los Alamos, we knew we were building a bomb. The whole bunch of us were building one bomb, All the parts must work together, and it must fit in a bomb bay, and we better get it done before the enemy who's working on it gets it, because if he gets there first, we're through. We knew we were working on a single one design, one single system. That made a big impression on me. Now, going to Bell Labs, I learned a great deal more. I told you about the episode of computing, a great many other ones. When I saw the nature of the system, I saw how when people did not see the system as a whole, they did counterproductive things, and that was very bad. I met them in Nike missiles. I saw again and again, we were designing systems. I'll come back to them a little later. Now, another point connected, I first learned with Nike missiles. When we put the test shots out at Kwajalein, I wasn't involved directly, but I was back home involved. I didn't go out to Kwajalein. What the heck? Why go out there for watch something go all bang in the sky? I found that there were field changes going out even as we were installing the plant to do the job. I didn't really realize how much a system is constantly being adjusted and changed and fitted here, there, and yon, and how field changes keep coming in even after the thing is accepted. Sometimes further field changes come through. It made me think a lot. Now, I'll come up with a second criteria. Part of a system engineering job is to prepare for changes so that when they occur, you can make them gracefully. Furthermore, if you do it that way, even as you're doing your research and developing the thing, when you get new ideas, if you've built it flexibly, you can. This flexibility I didn't appreciate for a long while, but it gradually came to realization. That's why in electrical engineering you draw black boxes. Then to some extent you can modify black boxes without affecting the whole system, but you also cannot. I saw that when doing calculation for people. Arguments like, look, there's no use putting a wide bandwidth processing circuit here when back there your radar data hasn't got that bandwidth. Or those servers haven't got the bandwidth, there's no use providing that bandwidth. A little bit more, yes, but 10 times as much, forget it. We have to look at how the flow of the information goes through, how much information is there, how will it be used. We have to think about these things carefully and not over-design one part and under-design another. So I began to understand these things from experience. Now I got another rule. The closer you hit design conditions, the worse it overload. To take the extreme example, think of a bridge built to support 30 tons, exactly 30 tons, optimally designed. Well, 30 tons and 1 pound and it falls down. Take a central office. We optimally design it for the maximum load. What happens when you exceed load? The whole thing is going crashing down. You get practically nothing through it. So one of the parts of design is graceful degradation when you exceed design specifications. The bridge sags a little bit more. We don't carry quite such a load, but we don't collapse immediately in a central office. Graceful degradation of the system under overload is essential. Now, system engineering, I told you, is discussed by lots of people, and almost nobody knows anything. But there is a set of notes written by my friend Bob Westerman, which was never published, but which I have a copy, and I've used parts of it. And he's the only guy I really think understands system engineering very well. And it's called One Man Systems Engineering, written back in '75, so this is 20 years ago. If I take the titles only, One Man System Engineering, what is systems engineering? On the objective, what does a system engineer do? The framework of systems engineering, organization of systems engineering, objectives and policy makers, on the methodology of system engineering, evaluation and common or uncommon sense, and the ending, envoy. Now, he believes that the group is the basis for system engineering. I had, when I was working with computers, essentially do it single-handed. There weren't people around in my location. There were people spread around the United States, and we got together at technical meetings. but fundamentally there weren't people who understood about computing, and I had to do system engineering by myself. And I ran into a lot of troubles. It's hard to do it, but I tend to be more than he does, but he had bigger problems, and he did not only military jobs, but Bell Lab jobs, and he did a lot of them. He believes that specialists brought together to form a team is the basis. But he also maintains that unless you let them go back to their specialty to keep their talents sharpened up, it will fail. And he apparently went through a period when, because he was part of a team who could solve all kinds of problems, they were constantly asked to put out fires, and they couldn't maintain their skills. So one of the things about system engineering is that the people with various skills must be given free time now and then to go back and sharpen up their skills in their various technical areas. They cannot be kept on a systems job one after another. They will lose their underlying skill. But management won't appreciate that point at all. They've got another crisis. Now, we believe that the system engineering job is never done. One reason is the presence of a solution changes the problem. And to give you my favorite example, I came to the belief that what I should provide in computing service was regular, reliable service, and particularly short times for debugging programs. In those days, you put the program on a machine, and you got the answer back. Now you have terminals, which does the same trick that I wanted to do. So I set aside an hour in the morning and an hour in the afternoon for short problems, up to 3 minutes. And if you ran 5 minutes, all right, but above that, off. No matter how much you say, I'll have the answer in 2 minutes more, forget it. Well, what some people did with 10-minute problems, they broke in 3 parts. They did 1/3, somebody else, they walked out of the office, computer room, somebody else came in with the next piece, somebody came in with the next piece, and bingo, they got the thing done. At a far greater workload on me, they were optimizing their personal production. My problem was to optimize the production of Bell Laboratories. And one of the first things you find out in system engineering is this classical conflict. The individual's idea of what they want individually and what you're trying to do, the system as a whole, comes head-on in conflict. And when you change the rules to design for our system optimization as a whole, they change their strategy for optimization in the small. For example, take how much you people have changed your plans as various rules for selection have been made. When management changes a rule for promotion, you change your behavior to fit. Not that you think that it will do best for the company as a whole or the organization, you think it's best for you. You continue trying to optimize your best response to the system every time the system changes. Therefore, system engineering job is never done. The moment you put in a new system, that people react differently. And so you got to design again. Second place, what happens is you design, you evaluate, you don't like it, you come back and you go around the circle, design, evaluation, quite happily, until somebody says, hey, we got to have a product. And some people with more nerve than mathematicians says, that's the deadline, we're starting this building tomorrow. And so you commit yourself to a design which you think that if you were left another 6 months, you could do better. It's not surprising, therefore, the product, when it's finally produced, is not optimal. The design, evaluation, and modification cycle is broken somewhere because it has to be. Theoreticians like me and the math department wouldn't have had the nerve to do it. Engineers are needed to stop the process and get it on the track. It's a very hard thing to do. Now, Westerman believes, as I do, that the client has some knowledge of the symptoms of his trouble, but he doesn't know the cause, probably. Your problem is to find out why he has the symptoms. Your problem is the same as the doctor's. You go to the doctor with a runny nose. The doctor's problem is to find out why. He can give you something to stop the runny nose, but that's not the problem. Now, the customer is suffering and wants relief, and he wants a relief immediately from his symptoms. But you know you'd better find out what the cause is. So you cure the cause and not the symptoms. Well, this starts very beginning, the trouble with the customer and the system engineer. Now, the system engineer has got some rights, but the customer has also. The customer, after all, is a man who is suffering. He wants relief now. He wants a missile tomorrow to shoot down those damn planes that come over. He doesn't want something designed in 47 weeks. So he is likely to be quite demanding. Let's have action now. Never mind all this analysis. Get me a solution. And the system engineer is in the position of the doctor to say, yeah, this guy knows the symptoms, but he doesn't know the cause. He doesn't really understand this problem. And part of the system engineer's job is to try to uncover the underlying problem. And it takes time to do this. It's rather time-consuming. Now, just as there's no definite system within which the solution is found, the boundaries of the problem are likewise elastic. What the hell the solution is going to be is variable. And I suppose the heart of system engineering is the acceptance that there is neither a definite problem nor a definite solution. There just isn't the thing which you were taught in school, definite problem, definite answer. The answer is 6. No. Now, can the schools do anything about the fact that they teach you no systems engineering worth mentioning? The answer is, I think, no. Attractive as the idea is of a laboratory course in system engineering, it can't be done. For example, consider my problem at Bell Labs in computing. I had to know the kind of people who were in physics, who I was going to educate. How educated were they? How much were they willing to learn computing? How could I lure them into it? I had to understand, as it spread out, the kind of people who were going to do what kind of jobs. I had to understand the ethos of the whole organization. How much duress can you apply in the organization, and how much must be by consent. There's an enormous amount of difficulty, and until you understand those elastic boundary conditions, the people who are going to do the job in the field. It's all very well to design something in the laboratory, which works beautifully under laboratory conditions with laboratory maintenance, but out in the field in real work conditions, it goes to hell rapidly. Because the people out in the field are in a hurry, they're under difficult conditions, and they aren't well trained. Well, I've watched it happen to many more companies than mine, because I didn't see it happen very often in Bell Labs, but I saw it happen elsewhere, where what worked in the labs doesn't work in the field. The people are different. They've got different styles. They've got different habits. They've got different work conditions. And what you can get done can't. For example, in a high morale organization, people work overtime without fussing. In a low morale organization, they're in at 8, but they're already drinking coffee, and if they're going to quit at 5, at 4:30 they're already prepared to quit, to get ready to leave right at 5 o'clock. Well, in an emergency, they still do it. A high morale organization, they behave differently. They come in and buckle down and get the job done. Well, you have to understand, what is the organization that's going to maintain this stuff? How is it going to be done? These are not easily taught in a lab class. Furthermore, the university doesn't have the faculty to do it, so I don't think it can be done. I think it has to be done the way Westerman said. You take people into a systems group, they live with the systems group, they learn by osmosis, and also, he believes, which is hard to do, you throw the older people out of the systems group to make room for the young. Now, somebody who's been in a systems group for some years is still doing fairly well, doesn't like being thrown out to take some young punk in who doesn't know. But you've got to do that. You've got to get rid of the older guys and get into the younger ones and keep the system going. You learn it by osmosis, by doing. Many a job you learn by doing, like bicycle riding, you learn by doing. You learn system engineering by doing, and I don't think there's any other way you can learn it. Much as I'm preaching to you now, it's a very hard business to learn. Now, if you look back at these lectures, I maintain that a fair amount has been this way. Oops. I seem to be a dedicated systems engineer. I seem to look at the system as a whole. I say I can't account for why I did it, but there I am. And these notes have been an attempt to show you the bigger system all the way along the way as best I could, but I really can't. You have to experience to know it. System engineering, if you don't mind the expression, is like sex. You can take a boy of 14 and let him read all the books you want. He isn't going to know what sex is. And when he has some experience, he still may not know what happened. Even if you take a person through a systems design, it may not be that they ever really understood what happened. But the only hope, I think, is to give them direct hands-on experience to find out. I don't think you can learn it from reading books anymore. You can learn sex from books. Yeah, you can learn something about sex, but you really won't learn what it is. Now, let me close with some observation about this business. I have seen many times the wrong problem solved exactly right. They didn't listen to the customer's agony. Or perhaps they listened to the symptoms but did not find the cause. And so while I patched those symptoms, some other ones broke out elsewhere. The nice solution to the wrong problem isn't very good. I would say, loosely speaking, it's better you have a poor solution to the right problem than a good solution to the wrong problem. And that means you get down somewhere near the bottom of what is the problem. Now, the problem always changes. There isn't any problem. And to give you an illustration of that, let's take my experience with Nike. When I got involved in it shortly after I came to Bell Labs, I was computing trajectories, and the problem was fundamentally, we're going to build something which will shoot down an incoming plane. Given altitudes, given speeds, and so on, given maneuverability, we got those estimates of what they will be when we get the system built, which of course we don't know, but we estimate those things. What altitudes, how fast, what maneuverability. We're trying to shoot down an individual plane. Well, we get it done. And sure enough, we take it out to quadrant. One plane flies across a drone, pretty much at an altitude we know, pretty much the right time. Boom, we shoot it down. One shot. Does that prove the system works? I don't know. All I can tell you is when they flew the film back, and I was there at Whitney watching the film, and the thing went off like a zing, and there was a big explosion in the sky and parts fell out. We all applauded and shouted, hooray! But one single shot, no one was coming by. How good was the test? It wasn't much. Well, let's go on. We now come to, shall we say, the defense of cities. How many batteries around New York? How many around Podunk? And how do we coordinate them? Well, how do we coordinate it? We can't have each one operating independently because then 6 of them all aim for the same airplane and the other airplanes come through free. Clearly, we've got a totally different problem now of coordinating the guns around the city or on a ship or anyplace else. We've got to coordinate the group as a whole. It no longer becomes shooting down one airplane by one missile. It now becomes defense against a fleet of targets. And the question of how long can you, having fired and guided into the ending, how quick can you launch another one to catch another guy further back? All these things have to enter into it. Well, we work on that for a while. We get that system going. So we have systems of missiles now. And now we come down, as I told you, the cities. What cities do you defend? Well, you think long enough, and you will say, we must leave no undefended target where he can do a great deal of damage. The enemy can do damage. We must make every bit of damage to the enemy equally painful to the enemy. That's what it really is. That's what the Nike missile is, an attempt. It's an attempt to make every possible target equally difficult to do us damage. More dangerous things to be lost, more it's defended. Something you don't matter, for example, a farm in Kansas, well, or if they destroy a farm in Kansas, you don't mind. If they destroy the capital of Washington, D.C., you do mind more. You defend according to the value you put on it, but you try to leave all targets equally defended. Now you see how enormous a difference that is from what we started out, namely to shoot down one plane. You see the solution, each stage brought the new problem. And that is the nature of systems engineering. It's never done. When you deliver the system and it's in action for a while, now the problem becomes deeper. And you see how in this case depth was achieved down to fundamentally. Now we could not have thought that simple answer. Every target must be defended equally. when we first began. Shoot down that airplane coming in at that rate with that maneuverability. That is what makes system engineering so difficult and why it is never done. It's an endless sequence around and around and around, and pretty soon you get people out of it because they're simply tired of it. I got tired of Nike problems after a while and went off and did other things. Other people carried on. But it's an unending task when you undertake systems engineering. Let me say again, but I don't think I said well enough. It's the patient or the customer who has the agony. He's got the pain. You do have to listen to him, but you've got to also put more in. You must try to find the cause. Same as a doctor. The doctor may have a great deal of trouble, so he may for a while give you some drugs to alleviate the symptoms. But if he's a conscientious doctor, he just doesn't relieve the symptoms. He tries to find the cause and finally do something about it. So I have nothing against relieving the symptoms immediately if there's nothing else you can do. But that's not a systems engineering job. The systems engineering job is to find out what the nature of the problem is, and each time you get a solution, your understanding of the problem should be deeper. You go around again, this system is deeper still. It's a difficult problem. Now, if you come back to what my favorite one for the last, say, 18 years or so, what is the educated person? It's a changing thing in the first place. But it's very, very difficult to get anybody to say much about what is the target. The complaint is that we got a bunch of people who can't do this, this, and this. Yes, they can't read, they can't do this, that, and the other. We know all the complaints. We don't really have a clear picture of what we're trying to do. It's one thing in the telephone business, although even there it's a little difficult sometimes to decide between supplying service and cheap service. We've done several things which we know really are not popular. For example, in my mother's day, in my childhood, you picked up the phone, there was a lady out there. Number please. And she did a lot of other things as well. She was a human being. Now you have great trouble in getting a human being on a telephone system. You punch buttons here, there, and yon, and it says, if you want one punch, if you want this punch button 1, if you want that punch button 2, and so on, bing, bing, bing. And half the time when you think you're getting a voice, you aren't. And that's not popular with people. People would like to have it, but that having real human beings there is very, very expensive. So what we have done, we've mechanized the thing, and we've produced a different kind of solution which isn't always popular. And in some corners of my mind, I wonder whether the telephone company has done the right thing, or whether it has gone too far automating and not enough, charge you a little bit more, but give you a little more human service. I want to close on that exact aspect. The trouble with system engineering is you are also required to think about the human beings. If you don't think about the human beings who are doing the job, it isn't going to run very well. My failure to notice when I put in the short test times that they were promptly going to change their strategies, I forgot that human beings were all eager to optimize their performance on their problem, and they didn't care one bit about the systems of how much computing was done for the whole of Bell Labs. My problem was the whole. Theirs was their individual one. And you will find throughout system engineering the conflict between the individual and the group. It's got to be solved. Now, solving group completely is not satisfactory because it turns out to be inhumane. You have to let the people get away with some things now and then. You have to let people act humanly instead of expect them to act like machines. It doesn't work when people are supposed to act just like machines. You have to appeal to some of their personal human features to make them like and work with the system. So system engineering is not only the hard engineering, which you have to have, and on the basis of which you are being trained now. We train you in school to solve definite problems in definite ways. And I've told you system engineering is not, it's vague problems solved vaguely. It's a big shock. But that's what I'm telling you is the nature of the thing. And I see no other way than telling you about it and then let you experience as you go through, looking at the system as a whole and realizing there is no total system. In your job, there is your position at the moment. There are people above and below, and there are various goals of the whole organization. But those goals of the organization change. For example, in many corporations for past decade or so, it's been very popular, maximum bottom line profit, quarter by quarter. Well, that neglected long-term growth. Attention to long-term growth meant there was no short pay, and you were bought up and you didn't exist further. If you can't stay in business, you're out. You've got to stay in business, and at the same time, you've got to think something about long-term profit. Now, almost every organization has changing goals. The role they play in society will change. We're expecting different things in society, so one of the things you must do to be a system engineer is be some sensitive to the human side of engineering. So next time we have a lecture on you get what you measure.